Okay, welcome to our introduction to thinking about continuous distributions. And so hopefully up to this point you feel pretty good about playing with at least the two discrete functions that we were playing with. And with those discrete functions we could figure out the probability of an event occurring, and then we could also come up with what our expected value is given the parameter estimates of how we've chosen to model the data. And so oftentimes, very often actually, we will be collecting data or measuring things that are not discrete. And we'll think about them as being on a continuous scale. And if you recall, when we were introducing the difference between discrete and continuous distributions are interesting in that we really can never know the true value of a continuous random variable. And that's because we can always get a more precise instrument. And so, if you're weighing seeds or whatever it might be, you could perhaps have a scale that goes to milligrams, and then that's the number that you would write down or put into your spreadsheet for the weight of those seeds. But then you could take those same seeds and put them on a scale that maybe goes to micrograms or tenth of a microgram or nanograms, and so on and so on and so on, so that any given value actually has an infinite number of significant figures. And obviously we can never know that, and so we're always going to be modeling data that we're going to treat as a continuous distribution, yet realizing that the values that we have are really a coarse estimate for what that real value is. And so let's start with the simplest continuous distribution to think about, just to kind of get our heads around some basic concepts with thinking about continuous distributions. And the distribution I want to start with is a uniform distribution. And so if we were to say take a random variable and say that and model it as being a random variable drawn from a uniform, we could formally write that as y is distributed as a uniform, and then A and B are generally the parameters for the uniform. And all A and B is minimum and maximum. And so this is very much how we use the vernacular, like pick a random number between 1 and 10. You're assuming that all of those numbers have the same probability until you observe them. And that's what the uniform distribution is describing. And so let's pop into R, and we can quickly look at the uniform. Let me move myself over here. And so there is a built-in function in R called unif, which shouldn't be surprising because R, after all, is a statistical programming language. So if I were to say question mark, let's say d_unif. Okay. So again, d_unif, just like we had d_binom and d_pos, now we have d_unif, which is going to be the density for a uniform distribution. And you'll see that the important parameters here are the minimum and the maximum value. And so let's go ahead and let's just look at that. So let's say that we want d_unif, and I want to know what the probability density is for 0.4, and then the minimum equals 0, and the maximum equals 1. And if I go ahead and I run that, I get that annoying warning message that R likes to spit at me. You'll see that the answer is 1. And now this is the really important difference between this is one important difference between discrete distributions and continuous distributions. When we were playing with discrete distributions, we had what was called a probability mass function, and it would tell us the probability of getting, whatever it might be, the probability of getting 3 bears in a hectare, or the probability of flipping a coin, and getting 8 heads out of 10 flips. Those were actual probabilities, and all of those probabilities sum to 1. With continuous distributions, we're dealing with what's called a probability density function. So instead of a probability mass function, which is going to give us actual probabilities, a probability density function will give us the probability density for any particular value. And so clearly the probability of drawing a 0.4 out of a uniform distribution bounded between 0 and 1, that probability can't be 1 because all the probabilities have to sum to 1. And so if the probability were actually 1 that you would get a 0.4, that would mean that it would be impossible for you to get any other values out of that. And we can, you know, so like if I were to say, well, what's the probability density that I would get a 6? It's also a 1. Boy, that's really getting annoying. It's also 1, okay? But again, these are probability densities. They are not probability masses. And this can, you know, similarly get a little bit more confusing perhaps. Let's say that we were to take, well, let's just take, what is the probability of drawing a 1 from a uniform distribution bounded by 0 and 10? And so if I do that, now the probability is 0.1. But again, these aren't, the probability density is 0.1, because again, these are not probabilities because there's an infinite number of possible values that we could put between 0 and 10. Right? I mean, we could go 1.00001, 1.0002. We could have all the possible values with an infinite number of significant figures, and they're all going to have the same probability density. So how do we interpret densities? Let's look at the uniform distribution, and hopefully it'll make a little bit of sense. I'm going to do what I usually do. I'm going to call up a plotting window so that way I can actually see what the heck I'm doing here. Okay, here's my plotting surface, and I will go ahead and that is the probability density function for a uniform distribution bounded by 0 and 1. And notice that the probability of getting less than 0 is 0. The probability density is 0. And the probability density of getting greater than 1 is also 0. The probability density of getting between 0 and 1, all of these heights here, the density, the height, are 1. And so 0 to 1 is 1. 0 density to 1 is 1. And this is why I start with the uniform distribution. It's super easy to integrate the area under that curve because it's 1 times 1, it equals 1. The area under the curve of a probability density function will always integrate to 1. It'll always include all of the probabilities. And so as before, when we were thinking about the cumulative distribution function, we can also think about what would the cumulative distribution function look like for a uniform. And all that's going to do is it's going to start integrating across from left to right until we have encompassed all of the possible outcomes. And so for a uniform distribution, the cumulative distribution function will look something like this. And so, and I had mentioned this to some people before when we were dealing with discrete distributions. This is why we have to get comfortable using that cumulative probability distribution, because there's no way that we can figure out the probability of getting exactly 0.5 from this particular distribution, because it'll have an infinitely small probability because there's an infinite possible number of values between 0 and 1. But what I can ask is, what does the probability say that I would get 5 or less? And we could do that by using the cumulative distribution function. And so I'm going to go ahead and I'm going to say punif. That's the function we'll use. And the quantile that I'm interested in is 0.5. And then the minimum is equal to 0. And the maximum is equal to 1. And that is 0.5. So 50% of the time, we expect that value to be 5 or less. Another nice thing about continuous distributions is we no longer have to worry about less than 5 or equal to 5 and less, because 5 itself is an infinitesimally small point on the number line. And so with continuous distributions, we no longer have to worry about, did Jim say less than 5 or did he say less than equal to 5? It doesn't matter, because 5 itself is infinitesimally small. And so the probability of getting 5 or less from a uniform distribution bounded by 0 and 1 is going to be 0.5. And so again, we can do the really easy integral calculus here. And we could say, well, here's our 0.5, okay? And so what we want to know is, what is the area under the curve from 0 to 0.5? And if we come down here and we go across, it's going to be 0.5. So again, the reason why I like to start with the uniform is it's a way that we can think about what we're doing with or how to interpret the probability density function, because again, it's not a probability mass function, and how to think about using the cumulative distribution function to think about the probability of a particular event occurring. And the area under the curve will always integrate to 1. So even if we were to go back here and we were to say, let's go back and use our density function. And I want to know the probability of getting, 0.25 out of a uniform distribution that maybe is bounded between 0 and 0.5. Well, now it's 2. The height of that rectangle is 2 because the width of that rectangle is only 0.5. 0.5 times 2 is going to equal 1. The area under a probability density function will always equal 1. And so that's why I start with the uniform distribution, because it's easier to do the integral calculus if you're just taking the area of a rectangle. And I'm all about easy integrals. But as long as we understand that that's what we're going to be doing with all of these continuous distributions, then we'll understand why we're using the cumulative distribution function to think about the probability of an event occurring. And we'll also hopefully understand that we do not want to interpret the densities as probabilities. It's simply, the density is just simply telling us the height of the curve at a particular value. Okay, now we'll go on to the normal. All right, let's think about the normal distribution, which is also called the Gaussian distribution. This is the old standby for general linear models. Most of the modeling that people do is usually based in one way, shape, or form on a normal distribution, at least with kind of, not really basic, but yeah, maybe basic experiments, basic analyses are based on a normal distribution. And so normal distribution, if we are going to assume that our random variables are drawn from a normal distribution, we could write it as, there's our random variable, it's distributed as a normal, and then there's two parameters in the normal distribution, mu and sigma. Okay, mu is the parameter. I'm even going to put it up here, parameter. The parameter mu is the population mean. Okay. Sigma is the population standard deviation. Sometimes this will be parameterized as the square of this, which is the population variance. Okay. These are kind of, they're not mathematically obviously interchangeable, but they're used interchangeably depending on how people want to describe the normal. And the variance is just simply the square of the standard deviation, which means that the standard deviation is simply the square root of the variance. And so those are our parameters, okay? And this is the population mean, the population standard deviation, and the population variance. And when somebody says population mean or population standard variance, that's the true value. We can never know the true value because if we're modeling things based upon random samples drawn from a distribution, that population has to be infinitely large. And obviously, we can't sample an infinite number of things to find out what the true population mean is. And so what we're going to end up doing is we're going to estimate those. And we estimate those, and that's what statistics are. Statistics. People think about statistics as being all the tests that you might learn and all the hypothesis testing. Those are statistical analyses. Those are analyses that you're doing of your statistics or on your statistics. The statistics themselves are our estimate of the population mean, so y bar, or maybe x bar, depending on what book you have. The standard deviation is simply shown as s. That is our estimate of sigma, and sigma is the true population standard deviation. So our estimate of sigma is our statistic for the standard deviation. And likewise, the population variance can be described as s squared. Okay, so again, these are statistics. These are parameters. Our statistics are our best estimates possible for the parameters. So we can think about what these two different parameters are doing. The mean is giving us some idea of what we can think of as being location, where we expect the majority of the data to be. And actually, the mean itself, we could think about as that is the expected value. If we know what the mean is of a population and we were to grab something, we initially would expect it to be the value of the mean, except we have this additional parameter, which is the standard deviation, which is telling us something about the spread of the data around the mean. And so we have two different parameters, one showing where we expect most of the data to be, and then the other one saying what spread do we expect to find around that. So let's go ahead and take a look at it real quick in our friend R, because I know that now we are all friends with R. And let's see, I guess I didn't want to throw myself all the way up there. I'll go back down here. Hey, I'm in the corner, see me? Okay, so when exploring distributions, there's a really handy function built into R called curve. And curve, as the name implies, will draw the curve that describes a probability density function. And so what I can do is I can call up, I disappeared. Oh, that's gonna be a problem. I'll just ignore me. Just pretend I don't exist. That's fine. Whatever. So curve, lowercase. Say I wanted the curve of the probability density function of a normal distribution. So that would be dnorm. That's the function that we would call up for the probability density function for a norm. And then within curve, I will just give it the value x, because it's going to figure it out. I'm not going to tell it what to do. But in this case, I'm going to give it a mean equal to 0 and a standard deviation equal to 1. And then by default, curve will only draw the curve between 0 and 1. And since I want to take a look at what this distribution looks like, I'm going to go ahead and say xlim equals c -3 from -3 to 3. And so I'll go ahead and I'll plot that, and let's take a look at it. And there is our friend, the normal distribution. Okay. The high point here is the expectation. That is the location. That's where we expect most of our data to be, is right there. And then the standard deviation is telling us something about this spread. And so this curve is generated through a probability density function. And if we were to go ahead and go onto Wikipedia and look up the normal distribution, there, right there, is indeed the probability density function for a normal distribution. Okay. And again, somebody else has figured this out, so there's no reason for us to memorize this, because you can always do a Google search if you really need to know the probability density function. The important thing being is that this function right here is what is drawing that curve. Okie dokie. Cool. And so what I'm going to do then is let's think not only about the probability density function, but let's also think about the cumulative distribution function. Because just like we saw with the Poisson and with the binomial, and now with the uniform distribution, we have a cumulative distribution function. And so this right here is just telling R that I want to set up a plotting surface where I'm going to have 2 rows and 1 column. And then I'm going to go ahead and I'm going to plot. Nope, that's not what I wanted. That's the uniform. Let's do this right. I want a d-norm. D-norm with a mean of with a mean of 0, standard deviation of 1. Don't need that. Don't need that. And this is going to be a p-norm. All right, now I might as well fix this too. Professional here. All right. And the x limits, let's go from -3, +3, -3, +3. Okay, sorry about that. Let's do this again. Let's get rid of that. And now we'll do this and this. There we go, finally. And so this is our normal distribution with a mean of 1 and a standard deviation of, or I'm sorry, a mean of 0 and a standard deviation of 1. And this is the cumulative distribution function. And all this cumulative distribution function is doing is it's integrating from -infinity to +infinity. That's all it's doing, right? And so it's just basically plotting the area under this curve as we move from left to right. And so that means that we could figure out the probability of any particular event occurring, or a range of events occurring. So if we want to know the probability of getting 0 or less, all we would have to do is integrate this part of the curve, and that's what the cumulative distribution function would give us. And so we could just go to 0, and then we could ask, what's that value? And spoiler alert, that value would be 0.5. And so let's look at how changing those parameters changes the shape. So I'm going to do that quartz window thing again. And spell it correctly. Quartz window thing. There we have it. And then I'm going to go ahead and I'm just going to run some code. And oh, that was it. Killing me. Okay. And so this again is the probability density function where you have a mean of 0 and a standard deviation of 1. And then here I have left the standard deviation the same, but I've changed the mu to equal to 2. And so now you can see that the highest point, the most probable value, is at 2. Standard deviation is the same. So all we've done is we've taken the same shape of curve and we've just shifted it to the right. Down here I've put the mean back at 0, but now I have a standard deviation of 2. And you can see that this curve now has much broader shoulders compared to this curve. And likewise here I've decreased the standard deviation to 0.5. And so now it's a much narrower or sharper curve. So with these two parameters, we can change not only the location, but we can also change the spread. And so that is the very brief introduction to the normal distribution. And what I want to do now is I want to dig in a little deeper to understanding how and why we estimate, or mainly the how, we estimate the location parameter mu, and we estimate the spread parameter, which is the standard deviation or the variance. And so on to location. Okay, the three most important words in real estate: location, location, location. So we're going to talk about location and how we estimate that from a normal distribution. So our estimate of mu, again, we're trying to estimate mu. The best we can do is, based upon our sample, we can come up with the best estimate possible for mu, is familiar to everyone, right? So our estimate of mu, which is y bar, is going to be what? It's going to be the sum from I equals 0 to however many observations you might have of all of your values of y divided by the number of observations, or your sample size. And so this is our nice little, I'll put a little dot here above that I. This is our best estimate possible for the parameter mu, which is just the arithmetic mean, the thing that we've probably been doing forever. Or not maybe forever, but at least probably since grade school. And again, just like with the binomial distribution, again, reminding ourselves that we're dealing with a probability density function. If you were so motivated, you could take this equation and you could take the derivative, the first derivative of it, and then you could solve for where that first derivative is equal to 0. And that's going to be the maximum likelihood estimate for the mean. And so when we're calculating the arithmetic mean, or just the average as we often think about it, all we're doing is, or what we are doing is we're calculating the maximum likelihood estimate. Nobody ever thinks about it as a maximum likelihood estimate, but it is the maximum likelihood estimate. And so it'll be an unbiased estimate of mu as long as all of our observations are based upon randomly sampled individuals. Okay, so these all have to be random variables. We couldn't have gone in and just, on purpose picked the 30 largest things and then calculated the mean and think that that's going to be the actual population mean. We want them to be true random samples, which also means that we want those observations to be independent of one another. So we don't want to make it more likely that, if you sample something really big and it's heavy, then you're going to kind of look for something that's small because maybe that was difficult. Then that would no longer be a random sample. And importantly, it's an unbiased estimate of mu if the population that we're sampling from actually is a normal distribution. If the population is not a normal distribution, then the mean will not mean what we want the mean to mean, and we don't want that, if you know what I mean, okay? And so we've already talked about the function in R to calculate such a thing, which is the mean, right? That is the name of the function. I think I have this set up now that I can hang out in the corner, and that way I can look at my code while I'm typing it. And so let's say that I'm going to grab just some numbers here. Those are numbers that clearly is probably not a normal distribution, but if we wanted to know the mean of that, all we would have to type is mean of y, and I probably should create y, and then that would be the mean, okay? Now, again, that only means something, if you know what I mean, if the underlying sampling distribution is actually normal. And so there are other location estimators that can be informative when describing your data. They just don't fit into the probability density function of a normal distribution. And the first one I want to mention is the median. And the median is simply the middle value of an ordered data set. So here we have an ordered data set of 1, 3, 7, 10, 100, 1,000, 1,001, 1,002. The median is going to be the middle point of that, which is probably going to be 100 because there's 3 values on one side and there's 3 values on the other. And so the built-in function for that, as you might imagine, is called median. And if I ask for the median of y, indeed, I get 100 right over here. Okay? And so the median is especially useful when you're trying to describe the location of a distribution that is not normally distributed. This is why, they don't talk about the mean average household income. They talk about the median average household income. because all it takes is a couple of people making a couple of $1 billion a year, and that skews up the whole mean, or it skews the distribution, which does screw up the mean. And then in that case, the mean wouldn't mean what we want the mean to mean, because most of our data won't actually be around the mean, it would be around the median. For calculating the median, if you have an even number of observations, so let's get rid of 1002. And so now there is no true middle value. What we do then is we would take the middle point between the two middle values. And so now with this new value of y, if I were to ask for the median, it's 53.3, which is halfway between 7 and 100. The other type of location that might be interesting is what's called the mode. And the mode for a discrete distribution is pretty straightforward. It's just simply the value that would occur most frequently. So if you were to make a histogram of discrete data, like number of bears in the forest or whatever it might be, it would be the highest point of that histogram. Unlike the mean and the median, the mode is unique in that it can, it doesn't have to be unique. You can have two modes. And so if I was to ask everyone in the class, hey, what's your favorite color? The most popular color that people would name would be the mode, but it's possible that the same number of people said blue as said green as said red, and then there would be 3 different modes to that, to those data. That's not true. There's only going to be one estimate of the mean, and there's only going to be one median. But with categorical, like nominal data, you can actually have more than one mode. Okay, and that's what people refer to when they talk about a bimodal distribution. It's a distribution with 2 peaks. That's what they're referring to. If your sample is nearly infinite, which would be great if you want to put in that much time to get an infinite size sample, and the distribution is truly a normal distribution, then the mean, the median, and the mode will all be the same. Okay, and so just be aware of that when you're describing data, that you want to make sure that the location parameter that you're communicating to people is actually communicating what you want to communicate to them. Okie dokie. And so that's the arithmetic mean, and I want to talk about 2 other types of means that mean something different depending on what your data are. And so, and I'm mentioning these because these do pop up. You will see them if you're reading the primary literature. You'll see them pop up, or you'll hear people talking about them. And they're kind of magical terms that a lot of times people don't really get an idea of what they are and why they are. And so there's 2 of these other types of means I want to talk about. The first is the geometric mean, and then we'll talk about what's called the harmonic mean. And so the geometric mean is simply the mean of the log of your data, and then you exponentiate that. So first you transform it into units of log, you take the mean of it, and then you back transform it to your original units. And we use the geometric mean when our random variable of interest is describing some kind of a multiplicative process. And so what do I mean by a multiplicative process? If you remember from general ecology, or if you haven't taken general ecology, there is a very simple population growth model called the discrete population growth model, and there's this parameter in the discrete population growth model called R, big R, kind of like the programming language, but in this case it's more similar because it's identical to, now that we're in the days of COVID, when people talk about what is the big R, and that's telling us whether or not the population of the disease is growing or whether or not the population of the disease is declining. And so to understand how and why it works, I've cooked up a kind of a sample kind of story problem where we can suppose that we are dealing with a population, and after the first generation, the population is going to increase by 10%, and then the next year, the population increases by 20%. And so let's go through and just go brute force through and calculate what do we think the average population growth rate could be. And what we can start with is let's see if we can predict how big that population will be after the second year. So let's start out and make it easy. We'll start out at the population size at time 0 to be 1,000. And so if that is the population size at the beginning point, the population size at the end of generation 1 then, this is generation 0, this is generation 1, we would take 1,000 and we would multiply it by what's called the net reproductive rate, 10% increase, so 1.1. So now our population size is 1,100. Next, we want to calculate what's our population size at the end of the next generation. So it's going to be N1 times, and now we have a 20% population growth. So our net reproductive rate is 1.2. And so 1,320 is what we would expect if we started with 1,000 individuals. The first generation had a 10% growth, and the next generation had a 20% growth. Now, if we wanted to know what the average rate of population growth is based upon those data, it would be incorrect to use the arithmetic mean. And so let's look at what the arithmetic mean is. We'll take the mean of 1.1 and 1.2. I'm going to assign that. And it's 1.15, right? The average between 1.1 and 1.2 is 1.15. So now let's go through and let's put that value into this little thought problem here. So now I'm just going to multiply it by the mean. And then for the next generation, I'll do the same thing, except I'm going to just keep doing it by the arithmetic mean. And so I'll go ahead and let's do that. And so now the expected population size is a little larger than what we know the right answer is. We know that 1,320 is the right answer because we went brute force through and put 1 point in for the first year and 1.2 for the next year. But what we'd like to have is just some measure of the mean, so that way we can just keep popping that same value in each time. And so now let's look at the geometric mean. So I'm going to create an object called gmean, and then I'm going to break this apart. So the first thing is, when we do the geometric mean, is we want to come up with the arithmetic mean of our data when our data are on a log scale. So I'm going to say that I'm going to take the log of 1.1 plus the log of 1.2. I'm going to take all of that and I'm going to divide it by 2. And so if I were to run that, that's the value I get. But that's not the value I want, because now I want it to go back into units of R. So what I've done is I've transformed the data, and we haven't even talked about transformations, but I've put the data on a log scale, I've calculated the arithmetic mean, and now I want to back transform it. And we back transform it. The shorthand for that is we're going to exponentiate it. And the function for that is exp. Move that back over. And so now the geometric mean is 1.1489. Remember, the arithmetic mean was 1.15 of those data, but the geometric mean is 1.148913. And so now let's repeat this little exercise that we had here, but now let's put the geometric mean into there. we predict that there's 1,320, which is the exact same answer that we got when we did this longhand. And obviously, if you only have 2 generations worth of information, go ahead and do it longhand. But, you know, if you had thousands of generations of information, which is entirely possible if you're looking at, you know, bacteria in a dish, you could have thousands of generations, we're going to want to use the geometric mean. And so the geometric mean is actually providing us with the information that we want, because the random variables that we collected were describing a multiplicative process. So that's, like in ecology, the geometric mean is used a lot when people are trying to model population growth, for example. Okay, so that's the geometric mean. The next one is the harmonic mean. And the harmonic mean is also, sometimes it's called the reciprocal mean. And what the harmonic mean is good for is when we're dealing with rates. And so let's use an example for this as well, because I think that if we just brute force through an example, it'll make sense as to why we would do this. And so, as an example, let the distance between 2 points be 100 kilometers. If you drive from point A to point B, you're going at 10 kilometers per hour because you're driving really slow. I probably could have said bike riding, because then it wouldn't have seemed, who cares? We can drive slow. It's Sunday morning. A to B at 10 kilometers an hour, and then we really bolt back and we'll go 20 kilometers per hour all the way back. And so how do we calculate what our average speed is? And so the incorrect answer would be to just take the mean of 20 and 10. Because the answer then looks like it would be 15 miles per hour. But it can't be 15 miles per hour, because clearly if we've gone from point A to point B at 10 kilometers per hour and point B to point A at 20 kilometers per hour, we were driving 10 kilometers per hour twice as fast as we were driving 20 kilometers per hour. So actually, our speed, our average speed, is 10 plus 10 plus 20 divided by 3. 13.33 kilometers per hour is our actual average speed. And so how we calculate the harmonic mean, it's simply you take the reciprocal. So instead of it being, instead of 10 kilometers per hour means it's 10 kilometers per 1 hour, we take the reciprocal of that. So it's 1 hour for 10 kilometers. And then we would add that to 1 hour per 20 kilometers. Again, we've taken the reciprocal of it. We can go ahead and we can take the arithmetic mean of that. And then we would want to flip it back over and take the reciprocal of that. And that is the harmonic mean. So again, we could do it really brute forcey, but you're not going to be able to do it really brute forcey when you have lots and lots of data. Or I guess you could, but it would take you hours to just type it all in like that. Or you can just simply transform your data by taking the reciprocal of it, taking the arithmetic mean of the reciprocals, and then back transforming it to the units that you observed it in. So our average speed is 13.33 miles per, or kilometers per hour. And so the harmonic mean you often see like when people are thinking about the rate of, molecular change across a phylogenetic tree. Like, what is the substitution rate where nucleotides are being switched out when people are doing genetics, for example? Those are expressed as rates. We have a rate of change. If we want to know the average rate of change, we would have to take those rates, take the reciprocal, take the arithmetic mean, and then back transform it. And then that'll give us the answer that we're looking for, because we're looking for the location, right? The actual location. And clearly 15 kilometers per hour is the incorrect answer to this problem, because again, we were driving at 10 kilometers per hour twice as long as we were driving at 20 kilometers per hour. The harmonic mean will fix that problem for us. So I just wanted to mention those other types of means, because you will see them pop up, and maybe in your own work you will look at the data and realize, hey, I'm actually estimating something that is determining a multiplicative process. Perhaps I should do everything as a geometric mean. Or maybe you're looking at rates, and again, if you're looking at rates, you should think to yourself, I definitely want to use a harmonic mean to describe this if I want to come up with the average rate that I've observed. And so that is the location. And next we'll think about spread and variability. Okay, spread and variability. And again, our location told us where we expect to see our values, and the spread and variability is going to explain how different those values might be from that expectation, from that location parameter. And so in a general sense, one easy way to describe to people what the spread is you could just simply provide the range, right? So it could be the highest and lowest value. It's like, this is how variable the data were. Or you could take a subset of that, maybe, the inner quantiles, which are often described as like, what is the range of values between the 25th percentile and the 75th percentile. And that'll give you some idea of how much spread there is in the data. And these are all very fine ways that you can describe the spread of your data to people. But since we're deciding, hopefully, if the data are right, that we are going to model our data as random variables drawn from a normal distribution, that's where we can use the variance. And again, the variance is just simply the expected variability around the location, right? And this is our parameter sigma. And so sigma, as I mentioned, is the standard deviation. Sigma squared is then what's called the variance. And the variance is simply our estimate of the variance, or assuming that let's just do it like pretending that we have an infinite population size. Let's go into theory land for a minute. Is going to be I equals 1 to n. And then what we're going to do is we're going to take each of those individuals, subtract it from the mean, and square it, divided by n. Okay, this is the equation for variance. If we look closely at what we're doing here, we're taking each value and we're subtracting it from its mean, and then we're squaring it. And the reason why we're squaring it is otherwise they'd cancel each other out, right? Because if you truly have a normal distribution that's in, the location, the mean is in the middle, you would expect there to be just as many values on one side as there are on the other side. And so if you didn't square it, they would all cancel each other out, and the numerator here would always be 0. And you don't want a numerator to be 0. And so we square it, and then we divide it by the number of observations. Okay? Which means that all the variance is it's the mean deviations, the mean of the deviations from the population mean. Because all we're doing is we're taking all of these values, squaring them, and then dividing it by the number of observations. And so this is very similar to the arithmetic mean. The arithmetic mean was talking about our data. Here, the variance is the arithmetic mean of how different all of our data are from the mean of that population. And so this works really fine as long as we have an infinite population size. And again, we're probably never going to have an infinite population size. And so we're going to have to estimate what our variance is based upon our sample. And that brings us to, actually, I messed up. That should have been sigma squared. But now what we're going to try to do is get my fingers really good and dirty, is our estimate of the variance. So s squared. But now we're going to put n minus 1 in the denominator. And this sometimes throws people off because it seems like magic. Like, why is there that n minus 1 there? Well, first of all, if you had an infinite population size, infinity minus 1 is still infinity. So it doesn't matter. So in the land of theory, based upon the probability density function, you know, our previous equation was fine. But here we're dealing with a sample. And it turns out that if you didn't have that n minus 1 there, this would lead to a biased estimate of your variance. And there's a number of really nice mathematical proofs showing why this is a biased estimate. But let's just use words to describe why this is a biased estimate. This is a biased estimate because we're trying to estimate the parameter sigma squared. But all of our observed data are going to be closer to our estimate of the mean than they are to the true mean. Because remember that all we're doing is we're estimating the mean. Y bar is just an estimate of mu. And so if it would make sense then that all of our observed data, all of these yi's, are going to be closer to our estimate of the mean based upon our sample than they are compared to the true mean. And so we put this n minus 1 in the denominator because that will give us an unbiased estimate. It doesn't mean that it's right, it just means that it's unbiased, and it's going to be our best estimate possible based upon our sample. And so this is going to give us our unbiased estimate. Another way to think about why we have n minus 1 here, and I find this to be a helpful way to think about it because it'll help us when it comes to thinking about degrees of freedom, is in order to calculate our estimate of the variance, we already had to estimate one parameter, and that parameter was our estimate of mu, right? Our sample mean is the first thing that we had to estimate, and then once we have that estimate, then we can estimate our estimate of the population variance. And so think about the fact that at the end of the day, we're always trying to model random variables. And random variables mean we don't know the value of them until we see them, okay? But since we've already estimated the mean, that means that if we had 100 observations, that 100th observation is no longer a random variable. If I told you that the mean of the population was 50, and I gave you the first 99 values, you could do a little bit of arithmetic and you could calculate that 100th value. So you've actually lost a random variable. And as we'll see when we start playing with building models, every time we estimate a parameter, we're losing a random variable, which is really what we're doing when we think about degrees of freedom. How many random variables are we actually dealing with? And so if this mean was based upon 100 observations, when we calculate our estimate of the variance, we no longer really have 100 random variables. We only have 99 random variables because we know the value of the 100th one because we used it to calculate the mean. And so we use the n minus 1 in the denominator. It's called Bessel's correction, named after Bessel, who's the person that first formalized that this is the way to come up with an unbiased estimate. But the two different ways of thinking about it again is that we know that our real sample is going to be closer to our sample estimate of the mean. And then also we can think about it so it makes sense to us maybe that we lose a random variable once we've estimated the mean. Because once we've estimated the mean, we know what that 100th value is, assuming that our sample size was 100. Yes, okay. The other type, well, that's all really that matters for the normal distribution. And then obviously once we've calculated our estimate once we have our sample variance, S is going to equal the square root of S squared. And that's our standard deviation. Okay, one last thing that people often use to describe the variability of their data, which is called the coefficient of variation. Coefficient of variation. coefficient of variation, or CV for short. The coefficient of variation doesn't have anything to do with the probability density function, so it's not necessarily a parameter that you're going to estimate, but instead it's just a way that you can describe the variability of your data. And in particular, it describes the variability of your data while accounting for what the mean is. And so the coefficient of variation is simply going to be the standard deviation divided by mu. So in our case, it's going to be S divided by Y bar. And that's all the standard, that's all the coefficient of variation is. And it's going to be unitless because standard deviation is going to be in whatever units we measured it in, and so is the mean, and so they're going to cross each other out, and it's just a unitless measure. A lot of times people multiply it by 100, so that way it's as a percent, but it's basically, it's unitless, so it doesn't really matter, and it's just a way to describe the variation, or how the variation might differ amongst different populations. So as an example, I have pretend data. It's not real data. Well, I'm going to simulate it. And that's what I like to do. But I'm going to pretend that I have a sample of 1,000 elephants and 1,000 whales. Okay? So I'm going to use the R-norm function, which is going to give me random normal variables. I'm going to say that I want 100 or 1,000 random normal variables. For elephants, I'm going to pretend that the mean weight of elephants is 10,000 pounds. And then I'm going to say that the standard deviation is 900. And so this is going to generate right here, that will generate 1,000 random draws from a population with a mean of 10,000 and a standard deviation of 900. And since I'm simulating data, I'll set the seed, so that way everybody will get the exact same answer. And then I'll do the same thing for whales, except here we're going to say that whales have a mean of 200,000 pounds, but we're going to give it the same standard deviation. And so if we were to look at then those standard deviations, let's look at the standard deviation of elephants, and then let's also look at the standard deviation of whales. Okay, they're both pretty darn close to what we said it was going to be, which was 900, which we would expect. And if you were to just look at the standard deviation, you would say whales and elephants are roughly equally as variable. And that's true around the point estimate of the mean, but it doesn't really tell us about how variable they actually are, given the fact that the means between those two things are so different. And that is where the coefficient of variation is helpful. And so we could calculate the coefficient of variation for elephants by simply taking the standard deviation of elephants and dividing it by the mean for elephants. And we will do the exact same thing for whales. Standard deviation of whales divided by the mean for whales. So we'll go ahead and we'll do both of those. And now we can look at the coefficient of variation. So the coefficient of variation for elephants is 0.09, and the coefficient of variation for whales is 0.004. And so even though the standard deviations are the same, whales are so much bigger that that same amount of variation is not nearly as big as if you were to look at something that was lighter, like an elephant, where you have a lot more variation. And just looking at these numbers, it looks like elephants are roughly more than an order of magnitude greater. Whales, elephants are more than an order of magnitude more variable than whales based upon these samples. And so again, it's a different way to describe the variability of your samples, and here you're accounting for what the mean is. Like an absurd example would be if this were the weight of elephants, and let's say that the standard deviation was plus or minus 1 pound, and then we were to compare that against a dog. Dogs. And dogs, let's say it's a random normal, where we'll sample 1,000 dogs, and we're going to say that the mean for dogs is, I don't know, let's make them kind of big dogs. They're good boys. let's say a 50-pound dog with standard deviation of 1. And so now they both have the same standard deviation, but the coefficient of variation now for elephants, I said dogs, I meant to say dogs. And we can go ahead and calculate the coefficient of variation for dogs. Come on, dog. There and there. Dogs is not found. There we go. And so now elephants have a really small coefficient of variation, and dogs have a much larger coefficient of variation. And that would make sense. If the standard deviation is 1 pound, but you're dealing with, you know, a multiple ton animal that varies by 1 pound versus a dog, which is only weighing 50 pounds and it's varying by 1 pound, clearly the dogs are more variable once you take the mean into account. And that's what the coefficient of variation is doing. So again, coefficient of variation isn't used that much for like statistical analysis purposes, but it's often a useful descriptor for the data, just to kind of characterize how variable the different samples are. So okay, that is our little foray into introduction to continuous distributions with a little bit of a deeper understanding of what's going into a normal distribution. And this will end part 1 of our intro to such a thing. And next time we will dig in a little bit deeper to the normal distribution and think about all the cool things that we can do with the normal distribution once we decide we're going to model our data as random variables drawn from such a normal distribution.